In this video, we'll continue with the next lesson in our module on logic and truth tables. We're going to introduce the idea of a truth set. So you'll see definition 1.1 is truth set. If P is a proposition over U, the truth set of P is T sub P equals, and then in set builder notation, you'll see we have the set of all elements in the universe, U, such that the proposition applied to the element is true. So we're going to let capital U denote our universe of possible inputs for our truth statement, and the truth set will be the set of all elements in the universe that make that proposition true. So an example would be, if the proposition is the set 1, 2 intersected with A is the empty set, and we take that as a proposition over the power set of 1, 2, 3, 4, meaning that the possible inputs for the set capital A are members of the power set of 1, 2, 3, 4, then the truth set is going to be the empty set, because when we intersect the empty set with the set 1, 2, we are empty. Or it could be singleton 3, because when I intersect singleton 3 with the set 1, 2, it's empty. Or it could be singleton 4, or it could be the doubleton 3, 4. There are no other sets in the power set of 1, 2, 3, 4 that have empty intersection with A. So it should be clear from that example that truth sets will depend on the universe. So here's another example. Over the universe of integers, the truth set of the proposition 4x squared minus 3x equals 0 is singleton 0. 0 is the only integer that satisfies the equation 4x squared minus 3x equals 0. And so it is the truth set. Singleton 0 is the truth set. However, if we expand the universe to be the rational numbers, we know that we can factor the left side. 4x squared minus 3x is x times 4x minus 3 equals 0. So we get the solution x equals 0, but we also get x could equal 3 over 4. So if we expand the universe to include the rational numbers, then the truth set becomes 0 and 3 over 4. When we're talking about algebraic equations this way, we'll often use the term solution set instead of truth set. But under the lens of logic, we can call this the truth set of the proposition 4x squared minus 3x equals 0. A proposition over U is a tautology if its truth set is all of U. A proposition over U is a contradiction if its truth set is empty. So, for example, if we let our universe be the set of rational numbers, then we'll find that the proposition s minus 1 times s plus 1 equals s squared minus 1, if we let that be the proposition P, then that proposition is a tautology over the rational numbers, because all of the rational numbers will satisfy this equation. Since it's true over the entire universe, or since its truth set is the universe, it's a tautology. On the other hand, the equation x squared minus 2 equals 0, if we let this be the proposition Q, then over the rational numbers, this equation doesn't have any solutions, because the solutions to the equation are square root of 2 and minus square root of 2, which do not belong to the rational numbers. So when we consider our universe to be the rational numbers, this proposition cannot be satisfied, so it is a contradiction. Truth sets of compound propositions can be expressed in terms of the truth sets of the simple propositions that make them up. For example, if A is an element in the truth set of P and Q, then A makes P and Q true. So this is true if and only if A makes P true and A makes Q true, which in turn is true if and only if A belongs to the truth set of P and A belongs to the truth set of Q, which is true if and only if A belongs to the intersection of the truth sets of P and Q. One more definition. Two propositions are equivalent over a given universe if the biconditional P if and only if Q is a tautology. In terms of their truth sets, that means that P and Q are equivalent if the truth set of P is equal to the truth set of Q. So here are a few nice identities. We already discussed that the truth set of P and Q should be equal to the intersection of the truth set of P with the truth set of Q. The truth set of P or Q then is equal to the union of the two sets, because if an element belongs to the truth set of P, then it makes P true. If it belongs to the truth set of Q, then it makes Q true. In either case, P or Q will be true. So that is the case. The truth set of negation P is the complement of the truth set of P. The truth set of P implies Q is the truth set of P complement union the truth set of Q. And the biconditional is the intersection of the truth set of P with the truth set of Q, the intersection of the complement of the truth set of P with the complement of the truth set of Q, and then take the union of those. So here we see a Venn diagram for the truth set of P implies Q, which we know from above is the complement of the truth set of P union with the truth set of Q. So for the complement of the truth set of P, you get all of this area, and then we throw in the truth set of Q, and this is what we get. All right. Here are some more examples. Take the proposition n plus 4 equals 9. Then over the set of integers, there's only one integer that satisfies n plus 4 equals 9, which of course is 5. So the proposition n equals 5 is equivalent to the proposition n plus 4 equals 9. And we know this because we've been solving these types of algebraic equations for many years. Just subtract 4 from both sides. To get the other one. Alrighty. We also have A intersected with singleton 4 is non-empty. That's equivalent to saying that 4 belongs to the set A. So over the power set of the natural numbers, these two statements will have the same truth set. If 4 belongs to some set A, then it will be true that A intersected with singleton 4 is non-empty. So these are equivalent propositions. And then implication, we know that if P implies Q is a tautology, then we use the double arrow for P implies Q. So since the truth set of P implies Q is what we saw above, it's the complement of the truth set of P union the truth set of Q, then this will clearly show that the only way for us to have a tautology, in a tautology everything would be shaded. The only way to have a tautology is if the truth set of P were inside Q. In that way, this was our universe, and we had the truth set of Q, and inside it we have the truth set of P. Then when we did the complement of the truth set of P, we would get everything outside of the truth set of P, and then we would do the union with the truth set of Q, and in that way we would get the entire universe. So the only way to say that the if-then statement is a implication with the double arrow is for it to be a tautology, and that occurs when the truth set of P is contained inside the truth set of Q. So here are some examples. Over the natural numbers, n is less than 4 implies n is less than 8. Because the truth set for the proposition n is less than 4, 0, 1, 2, 3, and 4, is a subset of the truth set of the proposition n is less than 8. Over the power set of the integers, the proposition that the cardinality of the complement of a set is 1. Now let's think about that. We're talking about the power set of the integers, so all possible subset of the integers. Any subset of the integers whose complement has cardinality 1, that means that that set includes every integer except for a single integer. We don't know which integer, but every integer except for a single integer is contained in this set A in order to make this proposition true. So that implies that if we intersect that set with the doubleton 0, 1, then the intersection will be non-empty. Because if our theoretical set A contains all of the integers except a single integer, then definitely it contains either 0 or 1 or both. And if A is a subset of the even integers, then that will imply that A intersected with the odd integers is empty. So now let's do some exercises together. We'll start with the universe, the power set of 1, 2, 3, 4. And we want to know what are the truth sets of the following propositions. Now, I want to think a little bit about the power set of 1, 2, 3, 4. We know that because the set 1, 2, 3, 4 has 4 elements, its power set should have 16 elements, and it's all of the possible subsets of 1, 2, 3, and 4. So I think it will be helpful if we go ahead and just write our universe over here off to the side. So one subset of 1, 2, 3, and 4 is the empty set. Or we could have any singleton set, 1, 2, 3, or 4. We also have the doubleton sets, 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. And we have all of the triples, 1, 2, 3, 1, 2, 4, 1, 3, 4, 2, 3, 4, And then finally we have 1, 2, 3, 4. We can double check if we got them all. There should be 16 elements here. And of course we do have them all. So now this I think will help us to find the truth sets for the propositions. So first of all, we're looking for any set A such that A intersected with 2, 4 is empty. Such a set will make the proposition true. So I'm going to say that the truth set for part A of this question is going to be, well, the empty set. Certainly when you intersect the empty set with 2, 4, it's empty. Or it could be the set 1, or it could be the set 3, or it could be 1, 3. Every other set contains either 2 or 4, so this is the full truth set for part A. For part B, we're looking for sets such that 3 is in the set and 1 is not in the set. So for part B, we could have singleton 3. Then it makes the statement true because 3 belongs to it, but 1 does not belong. Or we could have the set 2, 3, 3, 4, or 2, 3, 4. Notice that each of these propositions is a proposition that takes sets as inputs. So all of our truth sets are actually sets of sets. Next we have A union singleton 1 is equal to A. So what kind of a set would make this statement true? Well, it should be a set that already contains 1, because a set that already contains 1, if we do the union with singleton 1, we're not adding any new information there. So we're just getting back the set we started with. So this could be singleton 1, or it could be 1, 2, 1, 3, 1, 4. I could have 1, 2, 3, or 1, 2, 4, or 1, 3, 4, or 1, 2, 3, 4, the whole set. So this is the truth set for the proposition in part C. Part D, the proposition is A is a proper subset of 2, 3, 4. Proper subsets of 2, 3, 4, well, first of all, the empty set and the singletons 2, 3, and 4. And we could have 2, 3, or 2, 4, or 3, 4. So in fact, it's the entire power set of 2, 3, 4, except for the set itself. And the final proposition for this exercise is that the cardinality of A is equal to the cardinality of A complement. So again, we have to think about what kind of a set would make this proposition true. Well, we know that the universe is the power set of the set 1, 2, 3, 4. So if we're talking about a subset of 1, 2, 3, 4 that has the same cardinality as its complement, that should be a set that has cardinality 2. since the cardinality of 1, 2, 3, 4 is 4, if the cardinality of our set is 2, then the cardinality of its complement should also be 2. So these are going to be the sets 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. All of the doubleton sets in the power set. And if we think about the complement of 1, 2, it is 3, 4. So both the set 1, 2 and its complement have the cardinality of 2, and these are the sets that satisfy the proposition. So this is the truth set. In exercise 2, it says, over the universe of the positive integers, define P, Q, and R as given here, and then what are the truth sets of these propositions? So let's start with A. The proposition P is that n is a prime and n is less than 32. So the truth set for P should be the set that contains all of the positive integers, which are primes, less than 32. So this is 2, 3, 5, 7, 11. I'm just listing the prime numbers. It turns out that, of course, all prime numbers are positive integers, so we don't really have to worry about the positive integer part for this question. But we're looking for prime numbers less than 32. So 13, 17, 19, 23, 29, 31, and then I stop because if I find the next prime number, it will be larger than 32, so it will no longer satisfy the proposition. Then we can find the truth set of Q. Q is the proposition n is a power of 3. So we are talking about positive integers. Well, I could have 3 to the power 0, which is 1, or 3 to the power 1, which is 3. 3 squared is 9. 3 cubed, 27. 3 to the power 4 is 81, and so on. And finally, the truth set of R. R is the proposition n is a divisor of 27. So I'll look for the divisors of 27. Well, 1 divides 27. 3 divides 27. 9 divides 27. And 27 divides 27. So the divisors of 27 are 1, 3, 9, and 27. Then part B of the question asks us which of the three propositions implies one of the other. Well, R implies Q. How do we know? Because the truth set of R is a subset of the truth set of Q. So that means if you are a divisor of 27, then you must be a power of 3. And that makes sense because 27 is 3 times 3 times 3. Question 3. If the universe is the set 0, 1, 2, how many propositions over the universe could you list without listing 2 propositions that are equivalent? Well, let's remind ourselves that 2 propositions are equivalent if they have the same truth set. So since truth sets are elements in the power set of the universe, meaning truth sets are subsets of the universe, what the question is really asking us is, what is the cardinality of the power set of the universe? So the cardinality of the power set of our universe here is 8. We could list up to 8 propositions without listing 2 that are equivalent. All right, question 4. Again, we're given 3 propositions, P, Q, and R, and we want to find their truth sets. We're told that the universe is the natural numbers. So we're looking for, first, the truth set of the proposition Q, which is, the proposition is 2n is greater than 17. So if 2n is greater than 17, then n is greater than 17 over 2, which is equal to 8.5. Since my universe is the natural numbers, that means I can take 9, 10, 11, and so on. These will be the natural numbers that satisfy the proposition. If we think about 2 times 9, we have 18, and 18 is certainly larger than 17, so the proposition is true if n equals 9. If n equals 10, we have 20 is greater than 17, that's true, and so on. B, we're looking for the truth set of P and Q. So in order for an element to belong to the truth set of P and Q, it would have to make P true as well as Q true. So we can, off to the side, find the truth set of P. P are the natural numbers less than 4. So that's 0, 1, 2, and 3. So I need an element that will satisfy P, meaning a natural number less than 4, and will satisfy 2n greater than 17. And we know from the lesson that any such element will be in the intersection of the truth set of P and the truth set of Q. But we can clearly see that these two sets are disjoint, or they have no intersection. So the truth set of P and Q in this case is the empty set. Next, we're looking for the truth set of R. The proposition R is n is a divisor of 18. So the natural numbers which are divisors of 18 are 1, 2, 3, 6, 9, and 18. This is the truth set of R. The truth set of Q implies R. That's equal to the complement of the truth set of Q union the truth set of R. The complement of the truth set of Q is the natural numbers less than 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 6, 7, and 8 rather. Strictly less than 9. So we're looking for the union of this set with the truth set of R. So it should be 0, 1, 2, 3, 4, 5, 6, 7, 8. That's coming from the complement of the truth set of Q, and then in addition, from R, from the truth set of R, I get 9 and 18. And if we think about it, this makes sense because Q implies R is true when? Q implies R is true when Q is false, because false implies true is false, and false implies true is true, and false implies false is true. So those values are coming from this set. When Q is false, the implication is automatically true. When else is the implication true? When Q and R are both true. And that is 9 and 18. All right. Next, suppose that S is a proposition over the set 1, 2, all the way up to 8. If the truth set of S is 1, 3, 5, 7, give 2 examples of propositions that are equivalent to S. So the first thing that comes to mind, 1, 3, 5, and 7 are the odd numbers in the set 1 up to 8. So we could say n is odd. And because our universe is just the set 1 to 8, if we wanted to find all of the elements of the universe 1 to 8 which are odd, we would get exactly 1, 3, 5, and 7. So this is equivalent to the proposition S. One other thing that we could do is we could have the proposition be an equation. It could be something like n minus 1 times n minus 3 times n minus 5 times n minus 7 equals 0. When is this proposition true? Well, this proposition is true exactly when n equals 1, because then I would have 0 times these other numbers equals 0. Or when n equals 3, because I would have 0 here times the other numbers is 0. Or when n equals 5, or when n equals 7. So these are just 2 examples of propositions that have the same truth set as S, and having the same truth set as S means being equivalent to S. Now, determine the truth set of the following propositions over the positive integers. So again, our universe is the positive integers. We have 2 propositions. First, n is a perfect square and n is less than 100. Second, the cardinality of the power set of A is equal to n for some set A. All right. So the truth set for the proposition P is going to contain any natural number, which is a perfect square, rather any positive integer, which is a perfect square and is less than 100. So the positive integers, of course, are 1, 2, 3, and so on. Which of those are perfect squares? Well, 1, 4, 9, 16, 25, 36, 49, 64, 81. This is the square, these are the squares of 1, 2, 3, 4, 5, 6, 7, 8, and 9 respectively. The next perfect square would be 100, but our positive integer is less than 100 in order to make our proposition true, because it's and, so we need both of these to be true. So we're going to stop here. This is the truth set of P. Q is the proposition a positive integer is equal to the cardinality of the power set of A for some set A. Well, what do we know about power sets? What do we know about the cardinality of power sets? The cardinality of the power set of a set, it depends upon how many elements are in the set, and it's 2 to the power n. So for example, a set that has 2 elements is going to have a power set with cardinality 4 because it's 2 to the power 2, which is 4. So the possible cardinalities for power sets are powers of 2, 2 to the power 0, 2 to the power 1, 2 squared, 2 cubed, 2 to the 4th, and so on. So that's equal to 1, 2, 4, 8, 16, etc. So these are the possible positive integers that could be the cardinality of the power set for some unknown set. In part B, we are asked to determine the power set of P and Q. So the power set of P and Q, we know, is the intersection of the truth set of P and Q is the intersection of the truth set of P with the truth set of Q. And we know the truth set of P and Q. So where do these intersect? These intersect in 1, 4, 16. Are there any other elements in the truth set of P which are in the truth set of Q? 64 should be a power of 2. That should be 2 to the 6th power if we had kept going. So this should be all of them. The next one, the next perfect square, is going to be larger than 100, so no longer in the intersection. All right, finally, let's take our universe to be the set of integers, script z. Which of the following propositions are equivalent over the universe of integers? Well, it might help if we knew their truth sets. So let's think about the proposition A. A is the proposition 0 is less than n squared is less than 9. Our universe is the set of integers. That includes positive and negative integers. And we're looking for integers such that when you square them, they're between 0 and 9. So I know that 1 squared is 1. That's between 0 and 9. 2 squared is 4. That is also between 0 and 9. Then if I go up to 3 squared, it is equal to 9, so I can't include it because I need to be smaller than 9. But I could also have negative 1 squared, which is 1, that's less than 9, or negative 2 squared, is 4, that's less than 9. And that should be all of them, because again, if we get to -3, it's equal to 9, and we have to be less than 9. If we included 0, we need to be larger than 0, so it's just these. The proposition B is 0 is less than n cubed is less than 27. So let's think the same way. 1 cubed is 1, so it's between 0 and 27. And 2 cubed is 8, so it's between 0 and 27. But if I get up to 3 cubed equals 27, so I can't include 3. What about the negative integers? Well, -1 cubed is -1. And -2 cubed is -8. So since I need to be larger than 0, this should be all of the possibilities. And then the proposition 3, 0 is less than n is less than 3. And that's clearly just the integers 1 and 2. So now we are asked which of the following propositions are equivalent. Being equivalent means having the same truth set. So B and C are equivalent over Z. This is the last example that we have for truth sets. So we'll conclude this video here, and then we'll have one more lesson in logic.